Welcome, student, to the lecture series Complex Analysis with course code MAT 18R 4026 from the Department of Mathematics, Kalasilingam Academy of Research and Education. So this is the second lecture of Block 1 and Unit 1.1. So as we discussed in lecture 1, how do we define complex number and its algebraic operations like addition, subtraction, multiplication, and division. So I gave you 4 homeworks for that, and these are the answer. You can check with your answer. I hope this is very easy to understand and also very easy to do. Now I will start the second lecture on this. First one, I want to discuss about the powers of the imaginary I. So powers mean I am talking about only integer powers. It may be positive or negative. Okay, let me zoom the screen so you can see. Okay, here it is. So what I have considered here, I and its integer powers. So first one, this is the power index 1. So I to the power 1, that becomes I. So in simplified form or in complex form, we can write it as 0 plus I. So the real part of I is 0 and imaginary part is 1. Again, if we consider the square of I, that is I square, we all know it is equal to minus 1. So it has only a real part, and obviously every real number can be represented as a complex number also. So minus 1 can be represented as minus 1 plus 0 into I. Suppose you have a as your real number and you want it to be represented as a complex number. So how you can write it? A plus 0 into I. So this is the way of representing a real number as a complex number. Similarly, I have left the box blank here, but I want you to fill it up. Suppose I'm just explaining one more example, I cube. So what will be I cube? I square into I. So I square equal to minus 1. So minus 1 into I. So ultimately, the result will be minus I. And in simplified form, we can write it as 0 minus I. With this way, we can completely fill up this blank. I want you to do this, student. Please do it at your home. So in the next slide, let me fit it. Okay. So the next discussion is about power series. So an important function f of x equal to the power x, as you all know from our school algebra or school mathematics course, that e to the power x can be represented as an infinite series like this: e to the power x equal to 1 plus x plus x square divided by 2 factorial plus x cubed divided by 3 factorial plus dot 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 dot, and its nth term can be represented as x to the power n by n factorial. So for each real number x, this infinite series on the right hand converges to e to the power x. Okay, so the definition of power series is given here. I would like to zoom it to you. Okay, few times. Yes, here. this is the definition. Suppose you are considering x as the variable of an infinite series, and a series is written in the form as a0 plus a1x plus a2x squared dot 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 like this. So as a whole, we can write it as summation n equal to 0 to infinity an x to the power n, where an is complex number and x is also a complex number. So if it is a complex number, then we will say that it's complex power series, and if we restrict ourselves to a real number, then it's a real power series only. So since we are in complex analysis domain, we will consider an and x both as complex number only. So this is a power series around origin. Okay, origin means 0. Now if we generalize it, then we want to define a power series around any complex number c. So how you define it? This is nothing but we'll simply replace x by x minus c. So what will be the ultimate result then? Summation n equal to 0 to infinity an x minus c whole to the power n. If we express this, we'll get expand this, we'll get a naught plus a1 into x minus c plus a2 into x minus c whole square plus dot 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 an x minus c whole to the power n. This is the nth term of the series, infinite series, plus dot 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 dot. Okay, here obviously c is a constant, and all other terms like ai's and x can be considered as complex numbers. Okay, so next is this. So there are I have placed two examples of power series. The first one is around origin. So this is, I have written it as here summation n equal to 0 to infinity x to the power n divided by n factorial. So if we break this summation and expand it, so what we will get? 1 plus x squared by 2 plus x cubed by 3 and so on. So this is a real power series around origin or centered at origin. And another one I have given as around the number -1. This is given as summation n equal to 0 to infinity minus 1 to the power n into x plus 1 whole to the power n. So here we can see that coefficient of this power series, that is an, is equal to -1 whole to the power n. So when n is an odd number, it will give you -1. Other way, when n is even, then it will give you +1. Okay, so if we expand this, summation, we'll see. Suppose we have to start with n equal to 0. So if we put n equal to 0, that will give you 1. The next term will be n equal to, we have to put n equal to 1. If we put n equal to 1, we will get minus 1 to the power 1, that is -1 into x plus 1 whole to the power 1, that is x plus 1. So ultimately minus x plus 1. And following this rule, we will get the series as it is written here, x plus 1 whole square minus x plus 1 whole cube, and so on. So this is an example of a power series centered at -1. Another example, it's a power series centered at 1. I have written as summation n equal to 1 to infinity 1 by n x minus 1 whole to the power n. So here the coefficient of this series or power series is taken as you can see 1 by n, and I have avoided summing the sum starts from 0, since 1 by n is not defined at 0. So the summation started from n equal to 1. So this is also admissible in power series. So you can start from any finite number, not necessarily n equal to 1. You can also start from n equal to 2. Suppose you are defining an equal to 1 by n into n minus 1. Then we can see that this an is not defined for both n equal to 0 and n equal to 1. So the power series will be starting from n equal to 2 onwards. So this is admissible. You can start from any finite number. Suppose you want to start from 10, 20, that also admissible, but it is not a general practice. So mostly we start from 1 to 0, limited to this only. So this example is of a power series, starts from 1, and we have taken it as 1 by n, x minus 1 whole to the power n. So if we expand this, we'll get x minus 1 plus half into x minus 1 whole square plus 1/3 x minus 1 whole cube, dot, 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 dot. So, okay. So let me again zoom my window. So this is a very interesting example. It's in function basically, the exponential curve. So how we define exponential curve? Y equal to e to the power x, that all of us know. Okay, so if we plot it, so this is the plot, the blue line. As we can see, we all know when x equal to 0, y equal to 1 in this case. This is also depicted in the figure. So this blue curve depicts y equal to x, and this red line is nothing but the slope of y equal to the power x at x equal to 0. So we can see that the slope at x equal to 0 appears to be 1 here. So it is very simple to follow this. Simply consider the definition of derivatives at x equal to 0 for this curve. Then we will get this limit h tends to 0, e to the power. This is from the definition of derivative. I assume all of you know this definition in real derivatives basically. So after performing this limit, we will get the value to be 1. The slope of e to the power x at x equal to 0 appears to be 1. Okay. Now we want to find out the general formula for the derivative of y equal to e to the power x using the definition of derivative. So I'm starting from d dx of e to the power x. This is nothing but limit h tends to 0, e to the power x plus h minus e to the power x divided by h. Okay. Now here h is the running variable. So for any constant or any x, fixed x, so we can take e to the power x outside of this limit, since h is the variable, the running variable. So after performing this, limit, we all know the formula of limit h tends to 0, e to the power h minus 1 divided by h equal to 1. So ultimately it becomes e to the power x into 1. So e to the power x. So it is very interesting function. Derivative of e to the power x becomes e to the power x itself. So if you continuously differentiate this function also, the function will not change. So e to the power x will remain the same upon derivative up to any order. So this is very interesting example. Now, as I was discussing, e to the power x is its own derivative. Now we incorporate the chain rule over here. So d dx of e to the power u can be written as, here u is the variable or a function of x. So derivative of e to the power u, so when we will differentiate it, we have to consider u as x. So e to the power u will be e to the power u, as we know the derivative of e to the power u will be e to the power u. Since we are considering u as to be a function of x, so a multiplication into the derivative of u, it is e to the power u into du dx. Now we can use this formula to find the derivative of this. So these are some well-known formula. We know okay, this is very easy to compute. Incorporating chain rule, we can find all this rule. I want you to do this. And again, just one example, as I was saying, I will definitely describe one example here. Suppose consider y equal to log of x. Okay, then dy dx equal to 1 by x. Now, since x equal to e to the power y from the mother equation, so ultimately it can be written dy dx equal to 1 by e to the power y. So ddx of e to the power y is nothing but ddx of x from this equation only. So ddx of e to the power y means again ddx of log x equal to 1 by x, that we know. So now we have to employ chain rule over here, ddx of e to the power y. So e to the power y will come out basically, since the derivative of e to the power y is y itself, e to the power y itself. So e to the power y into derivative of dy dx, that is equal to 1. So e to the power y and ddy x equal to log of u into 1 by u into du dx. Okay, so this is the ultimate formula. This is how we have to do all this formula. And here also ddx of log of x equal to ddx of log x by log to the base 10. This is how to do. I have described it over here. Okay, formula for derivative of log of any base other than e will be like this only. Since derivative of log to the base e x, log x to the base e is 1 by x, and other if you change the base, so this is the formula you have to follow. So with this, I want to stop today's lecture, and we will all see you in the next lecture. Thank you.